The effects of caffeine on information processing in the perceptual motor system. Our proposed research aims to address the question, how does caffeine affect the overall speed of the visual perceptual motor system? Caffeine is a psychostimulant, known to affect the function of the central nervous system. Consumed daily by more than 70% of people in Australia, caffeine works by stimulating attentiveness and performance of the nervous system. At baseline, we will use a FITS task to measure the rate of the visual processing system under varying degrees of difficulty or uncertainty. We will use the same set of tasks to measure how this rate of processing changes due to the consumption of caffeine. It is hypothesized that caffeine will lead to a significant increase in the average rate of visual information processing, or more specifically, the rate at which we can resolve uncertainty in the visual field. As a means of control in this experiment, we printed each condition or target difficulty onto paper and fastened each set of targets to a secure table by taping down the vertices. Each condition was placed in order of difficulty from lowest to highest. The experiment was conducted in a quiet study room in the Curtin University Library. We ran 5 trials for each of the 6 conditions for each participant. The order in which the participants completed each of the 30 trials was randomized by a 6-sided die, each number indicating which condition would be completed on each trial. If the same number was rolled twice in a row, the researchers would roll the die again, ensuring the participants would not complete the same condition twice in a row, and thus decreasing practice effects. An automated ready, go audio from the internet was played to initiate each trial. This was played 3 times prior to the experiment for each participant to ensure that each participant was aware of the time between ready and go. To measure the time in which each trial was completed, we used the standard stopwatch on an Apple iPhone. The timer began at go on the audio and was stopped when the stylus hit the final target. The mean time for each condition was used to equate the speed in bits per second and time per target, which was used for our analyses. Absolutely no caffeine was to be consumed by the participants on the day of pre-manipulation trials. One researcher observed each participant to determine whether any mistakes were made in each trial. 2 days after the baseline trials, we used the same participants to test how these reaction times were influenced by caffeine. Each participant was required to abstain from any form of caffeine for up to 24 hours prior, and each experiment was conducted after 12:30 p.m. Each participant consumed 1 single shot flat white coffee with no sugar exactly 20 minutes prior to their set of trials.
Moving on to the results section. It's firstly important to define what we are describing so that a more coherent grasp of the results analysis can be communicated. The 3 graphs represent the average time taken per target in seconds on the y-axis and the difficulty in bits on the x-axis for baseline and after caffeine ingestion for the Fitz's test. The y-intercept, referring to the number either added or subtracted from the slope in the regression equation, is a quantity that describes a measure of overall speed of the perceptual motor system for a participant. An increase or decrease in this value after manipulation will tell us whether the perceptual motor system was faster or slower. Alternately, the slope is the value paired with the x in the regression equation. This relates to the rate at which uncertainty is resolved with regards to the difficulty for each trial, either baseline or manipulation. Essentially, the slope of the trend line determines the rate at which the trials were conducted as a function of the difficulty. So putting these 2 parts together, you can assign a difficulty x and get a time per target in a trial, which would be your output. The 2 solid lines on each of the 3 graphs represent this. The r-squared values are defined as the variance in y that can be explained by the regression line, or put another way, to what extent y can be explained as a function of x. So r-squared in our case is how much the time taken per target can be explained as a function of the difficulty. A higher number out of 1 in our case correlates to a larger extent that difficulty explains time per target. Bits per second was the term used to define information processing and was calculated by dividing the difficulty in bits by the average time taken per trial. It is another way of describing the change of rate of processing or solving uncertainty for this experiment. Okay, moving on to the graphs. For participant 1, it can be seen in the first graph that the baseline data, coloured blue, the y-intercept is negative 0.046. Comparing this to post-caffeine ingestion, coloured red, the y-intercept was negative 0.059. So in theory, it could be said that caffeine resulted in a 0.013 second increase in speed of the perceptual motor system of participant 1 when the uncertainty is 0. However, this would be an invalid prediction, as explained beforehand. The slope of the linear trend lines for participant 1 from baseline to post-caffeine decreased from 0.128 to 0.106. As slope is a rate that determines output, a decrease in the slope correlates to a lower or faster time for resolved uncertainty. In the case of participant 1, this relates to roughly a 17% decrease in time taken, so a 17% faster rate of processing under the influence of caffeine. The R-squared value for baseline for participant 1 was 0.93, meaning that 93% of the data could be explained by the variance as a function of x. The variance of the caffeine trials for participant 1 was 0.98, meaning that 98% of the output could be explained by the difficulty. So under the influence of caffeine, the actual data was more aligned with the trend line than baseline for participant 1. So lastly, for participant 1, we have the average bits per second for each of the trials. We can see that the average bits per second at baseline was 0.99, and after caffeine it was 1.26, meaning an increase in information processing, which is consistent with what was represented on the graphs and also consistent with what we hypothesized. Okay, moving on to participant 2. The second graph represents the data collected for participant 2 at baseline, again in blue, and post-caffeine in red. The y-intercept for baseline was 0.04 and for caffeine was 0.052, showing a theoretical increase of 0.048 seconds for the perceptual motor system at no uncertainty. As stated before, it is questionable whether this can be extrapolated given the data that we tested was limited. The slope for participant 2 showed a considerable reduction in resolved uncertainty, with baseline being 0.102 and post-caffeine being 0.065, indicating roughly a 36% decrease. It can then be said for participant 2, resolved uncertainty under the influence of caffeine was 36% faster than no caffeine. The R-squared value for participant 2 was 0.95 for baseline, indicating quite a high percentage of the data that can be determined by the difficulty. And the caffeine R-squared for participant 2 was 0.93, meaning that 93% of the variance in the time could be explained by the difficulty. Lastly, for participant 2, we have the information processing tables. So we can see at baseline here, the average bits per second was 1.08 for participant 2, and then after caffeine, their average processing rate was 1.36. Again, consistent with the data that we measured. The y-intercepts, again in blue for baseline and red for caffeine for participant 3, are a good example of how the y-intercepts for this experiment are a product of the calculated slope. As participant 3 experienced no considerable difference for bits or x equals 2, the caffeine y-intercept is positive 0.067 and baseline is negative 0.004, making it impossible to reference whether this will hold true for no uncertainty or 0 bits. The difference between them is 0.071, which in theory is a 0.071 increase in the perceptual motor system at x equals 0. Participant 3 experienced a considerable improvement on resolved uncertainty, with the slope of baseline being 0.103 and post-caffeine being 0.067, a 0.036 decrease in rate. This equates to roughly a 35% increase in resolve rate, meaning a 35% decrease in time per target for participant 3 under the influence of caffeine. The baseline R-squared value for participant 3 was 0.95, again indicating high determination between time per target as a function of difficulty. R-squared for post-caffeine was 0.87, meaning that the difficulty was 87% likely to determine time. Finally, for our analysis, we've got the information processing for participant 3. We can see at baseline the average bits per second was 1.1, and after caffeine, the average bits per second increased to 1.3. So overall, the information processing was consistent with what we hypothesized for all 3 participants.
The current study investigated the effects of caffeine on information processing by measuring reaction time to a FITS task before and after consumption of a single shot flat white coffee. The results yielded shorter reaction times for all participants after coffee consumption, providing support for the hypothesis that caffeine causes an increase in the overall speed of information processing and the perceptual motor system for each of the 3 participants. Observation of the regression line in both the manipulation and baseline conditions for all participants displayed a positive slope, indicating an increase in reaction time in seconds as difficulty in bits increased. The regression line for the manipulation condition indicated that for all participants, overall reaction time increased significantly after caffeine consumption. When observing the slope of the regression line for participants 2 and 3, it was identifiably less steep in the manipulation condition compared to the baseline. This indicated that under manipulation conditions, when difficulty in bits increased, there was an increase in the overall speed of information processing. When observing the slope of the graphs for participant 1, the steepness of the slope for the manipulation condition was quite similar to the steepness of the slope for the baseline, which differed in comparison to the differences in steepness of the slopes for pre- and post-conditions for participants 2 and 3. Potential explanations for the differences in results are considered. Participant 1 was the first to do the task and therefore had less familiarity with the task and less competitive motivation without having prior scores to compare to. Once the first set of scores were recorded, this set the standard of what the following participants would aim to match or beat. This may also have set the standard for participant 1 to aim to achieve better scores in the second set of trials in the manipulation condition and explain why their scores were lower in the manipulation condition compared to participants 2 and 3. The competitive bias could be avoided in future studies by having participants complete tasks separately and unable to see the scores. However, in this case, it was unavoidable as the experimenters were also the participants. This may also have contributed to participant 2 and 3 having higher baseline scores as they were able to observe the task prior to completing it and potentially familiarise themselves with the task and observe skills which would be useful in their own trials. Implications and recommendations. The results of this experiment were somewhat sensitive to individual differences, which are as follows. As different people operated the timer for the tasks, there may have been discrepancies in the reaction time of the person timing. This could be avoided by using one consistent electronic sensor-activated timer for all trials instead of a person operating a timer. Also, it was understood that different people can have different tolerance and reactions to caffeine. Some participants indicated a low tolerance to caffeine, which may have influenced their results to be faster than someone who had a higher tolerance and did not feel the effects of caffeine to the same extent. Recommendations for future studies would be to conduct trials with multiple levels of caffeine consumption and a measure of participants' regular coffee intake and self-measures of caffeine tolerance. Similarly, different people may have different physiological responses to caffeine, such as shaking hands, which could influence the task based on physical capability rather than ability to process information. In the future, perhaps those who experienced any physiological responses should be noted and excluded from the results. The results indicated that caffeine had a positive effect on increasing information process and the perceptual motor system, which is useful to understanding the benefits of caffeine for increasing performance in many physical and mental activities. It could further be considered in terms of performance enhancement in sports and where it should sit in terms of legal considerations in that area.